This is going to be kind of an extensive video in which we're going to explore the graphs of absolute value functions. And so we're going to start by taking into account the most basic absolute value function that we could ever create. And that would be the function given by the equation f of x equals the absolute value of x. Or another way we could say this is just y equals the absolute value of x. Now, recalling from what we have talked about in the past, absolute value of a number is really just saying is that number's distance to zero. So when we talk about absolute value, the thing that's important here to recognize is some positive number. Actually, let me just put it this way, is non-negative, because distances are always positive. So what we're going to do is we're just going to kind of create a basic sketch of this by coming up with a set of solution pairs. So I'm going to say x and then y, or we could say x f of x, the function value at x. And let's just put in a good set of domain values here. We say -2 to 2 going by ones, okay? And so plugging these in, I mean, it's just like any other function. If I were to say go find f of -2, what this means is we're going to take out our input, which is our x, and we're going to plug in a -2. It's just that when you find the absolute value of -2, it's just 2. So if we were to plug in -2, I'd get 2. If I were to plug in -1 into this function and say change this to f of -1, I'd put a -1 right here and I'd get just 1. As a matter of fact, we say, well, the absolute value of 0 is 0, the absolute value of 1 is 1, and the absolute value of 2 is 2. So you can see that all of these outputs here are non-negative, okay? And so we can have negative outputs, but as far as what comes out of an absolute value itself, if it's just absolute value, those will be non-negative. If they came out to be negative, it's because we did something to transform them. But going ahead and sketching these solution pairs that we found here, -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2, will give us an idea of what absolute value graphs look like. So I'm going to start with 0, 0, which is at the origin. And I'm not going to label these this time. I apologize, but we have 1, 1, 2, 2. If we were to plug in 3, I guess I would say this, we would get 3, 3, even though we didn't do it. And then on the left side, we say -1, 1. -2, comma, +2, and of course if I did -3, I'd get +3. But the thing that's important to recognize is that all absolute value graphs, every single one of them, they look like the letter V. So the one thing we want to write down right off the bat is this: absolute value graphs have a shape like the letter V. Okay, like the letter V. And this is going to be true for all of our absolute value functions. As a matter of fact, what we're going to do now is we're just going to go basically play around with this function and say, well, what would happen if I say took 2 times this, or maybe subtracted 5 off of this? What would this do to the original graph? But we essentially want to know what this graph looks like. And before we get any further into this, what I want to tell everybody is we can say, as a more general form to represent y equals the absolute value of x, we could rewrite this y equals the absolute value of x in general more along the lines like this. And I know this looks kind of like unnecessary, but we could say this was really 1 times the absolute value of x. And we said the absolute value of x minus 0 on the inside of here. Now keep in mind that anything minus 0 is just itself, so I guess that would say the same thing as this right here. And then I could even say plus 0 on the outside, but the reason why is because the 3 values we are going to be using to transform the original function right here to change the way it looks are these values a, h, and k, okay? And we'll get into those. But let's go ahead and start by taking a look at what would happen to our graph if I were to say, and if you notice all these here, we say g of x, h of x, and j of x. What if we were to mess around with what I'm going to be considering this thing we call the a value, this a value out in front of our absolute value bars right there, okay? And so we could accomplish this just by kind of, I guess, extending our table in this last example. Really, if you wanted to look at this, we say g of x. G of x, if you want to consider this, g of x is no more than f of x, but where we took all the original outputs and doubled them, okay? So instead of, say plugging in -2 and getting 2, imagine this. What if we were to say g of -2? We would get 2 times the absolute value of -2, which, simplifying this, we have to do what's inside the absolute value first. I get 2 times the absolute value of -2, which is 2. I would just get 4. So up here we'd say, well, instead of getting 2 for an output, we'd get 4 for an output. And then what if we put in -1? We say, well, what's g of -1? What's our y value when x is -1? Well, we'd say it's 2 times the absolute value of -1. Which is 2 times just 1, which is 2. So we could say I really could just double this right here. I say 2. If I doubled 0, I'd get 0. If I doubled this one, I would get 2. And if I doubled this 2, we would get 4. So essentially, if we were to sketch this graph, now looking at what we had drawn up here, we'd say 0, 0 would still be on this graph of g of x here. It's just that instead of having the point 1, 1 on our graph, say for instance on the right side, we'd have the point 1, 2 for a height. So we say 1, 2 would be here. We'd say, all right, 2, 4 over 2 up 4 would be right here. And then likewise on the other side of 0, 0, we'd say negative 1 would have gone to a positive 2 because we doubled the original y value. And negative 2 right here would have mapped on to a positive 4. So we say right here. And what we can see is we still get this V-shaped thing. It's just that what we're going to say happened is this. It got vertically stretched. Okay, so we can record this here. Vertical stretch. So far we've seen that this is a possibility that can happen there. Okay. What if now we were to go back and say letter B here, this is this h of x equals 1/2 x. I'll make a new table on this one just to be clear on what it is that we're looking at. But we say h of x, we say how about negative 2, negative 1, 0, 1, and 2. It looks like if we were to say, all right, we'll plug in, say 0. Well, the absolute value of 0 would be 0, and 0 times 1/2 is 0. So we still have this point 0, 0 on our graph. I'll even switch colors here. Let's do this. Let's go over to like an orange. But 0, 0 would still be on this graph right here. If we were to plug in a 1 though, imagine this, if you put a 1 right here, well the absolute value of 1 is 1, but times 1/2 we would get only 1/2. And if I were to plug in 2, well the absolute value of 2 is 2, but times 1/2 or times its reciprocal I would get 1. And the same thing's going to happen on the left side that we keep seeing on the absolute value graphs we've looked at so far. There's this idea that it's kind of symmetrical on both sides of the graph. Okay, so if I were to plug in a negative 1, well, it'd be the same thing as if I plugged in a positive 1 because the absolute value of negative 1 is 1. And take that times 1/2, I'm going to get 1/2 here. So we're seeing this symmetry pop up again and again. And again, I would get 1 here. So if we were to sketch this, we say, all right, well, 0, 0, but 1, 1/2. It's not very high off the ground. It'd be about right here. And we say 2, 1 would be right here. And going the other way, we'd say negative 1, 1/2 and negative 2, 1. What we see is that we get this graph right here that we would say it was not vertically stretched, but we could refer to this as vertical shrink. Okay, but in either instance, what you're noticing here is that our original graph was this graph in pink. If we were to put, say, an a value of 2 out front, all of a sudden I've got this stretched graph. It's the same shape, but it's a little bit skinnier. It's stretched. And if I were to put, say, a 1/2 out front, I've got this shrunken graph, but they all start at 0, 0. Okay. The last possibility we'll take a look at in this little snippet of a video, but is basically this. What if I had like a negative 1/2 out front? Now, would that affect these outputs right here? Now, earlier you heard me say that they should be non-negative, but see the thing here is this negative here is out in front of the absolute value bars. So again, let's just go ahead and switch colors over maybe one time to like a green, and then we can wrap this section of the video up here. But we say if I had x and we said j of x, we could say negative 2, negative 1, 0, 1, 2, just because they're convenient to pick. I am going to start by plugging in 0. We say j of 0. What's the y value at 0? Well, the absolute value of 0 is 0. 0 times anything, even negative 1/2 is 0. So we'd say 0, 0 is still on this graph. We're just messing around with a here, and a seems to not move our graph around. They all start at the origin, but what if I plugged in 1? Now, in this instance, we say, well, j of 1 would be negative 1/2 times the absolute value of 1. And, you have to do what's inside the absolute value first if you can. And we say, all right, well, this is negative 1/2 times a positive 1, which is a negative 1/2. So we actually got a negative output, but by no cause of our own. It's because of this negative out front. So it's not that the absolute value, that stuff came out to be negative. When we took the absolute value of 1, we certainly got a positive 1. It's just that we were taking it times a negative, which reverts it or flips it to negative. So we're going to basically get all the same y values that we did for h of x here, except for they are going to all be negative because we're taking it times a negative 1/2. So this is going to be a negative 1/2 here. This is going to be a negative 1. And when we sketch this, we say, well, 1, negative 1/2 would be about right here. And then 2, negative 1 would be here. Negative 1, negative 1/2, and then negative 2, negative 1. We get this graph right here. And you could see that it's kind of a x-axis reflection of, and it's not a very good sketch of, but of this orange graph. Okay, so a few things that we could determine about A before we wrap this video up. We say, well, can we make any statements about the effect of A upon the value or the graph of the absolute value functions? And I think that there are a couple statements that I do want to make here. First one is this. We say if A is greater than 1, then we say we had vertical stretch. Okay, this is true. If, though, we say A is some number between 0 and 1, that is a proper fraction, we're going to have what we call vertical shrink. And we saw that, in observation there with that half out front. Half is a proper fraction. So it caused our graph to have vertical shrink. Okay, so vertical stretch, vertical shrink. I think that we could write this one here. We say if A equals 1, then it's the same as a normal absolute value of x graph. So same as the original one we had drawn up here when we just graphed y equals absolute value of x. Okay. Furthermore, we say, well, what else did we conclude? We say if a is less than 0 or negative, when we write this down, then it opens down. And furthermore, we say if a is positive, then it opens up. Okay, I want to be really clear on this though before we move on, but basically we could say that all absolute value graphs are these V's where this beginning point, we're going to refer to this as its vertex. Okay, and also they have this imaginary vertical line that runs through the vertex, and we're going to give this a name. This is called the axis of symmetry. And the axis of symmetry is always a vertical line that does go through the vertex. So in this case, all of our vertices were at 0, 0. But let's be clear on this. The vertical line here would have to have an x equals a number equation, because we know vertical lines always are x equals a number. But it would have to be the same exact x value as your vertex, which is a kind of a convenient thing. So when we graph these things, we are always going to be identifying where the vertex is, but also the axis of symmetry. And last but not least, the last thing I want to point out here is this, the a value. Now the a value, we notice that it does these things, but I guess we could be, kind of summary about it. Like we could summarize this. But I noticed that when my a value was 1, that is when I graph my original 1 times the absolute value of x, that's this guy up here. Notice that our pink graph went up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1 from its vertex to the right side, okay? So that a value really is kind of slope-ish. It's a slope, kind of. It's not really a slope, but it tells you how from the vertex to move on the right side of your graph to get what the right side looks like. And the nice thing about that is once you know what the right side of your graph looks like, we have this idea that all absolute value graphs look like V's, and so they are symmetrical, and we could get some points on the left side. Same thing for this graph of g of x. We said the a value is 2. If I were to write that as a slope, notice that from the vertex we went up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1. And even further we say, well, what if I had this vertical shrink right here? This a value was a half. This was our orange graph here, but if you look at the orange graph, I went up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. So lots of things we can say about absolute value graphs in general, but also about the a values. So in the next video, we're going to look at translations or shifts on our graphs.